Bismillahirrahmanirrahim. Welcome to Pakistan International School Taif. Now students, we are starting lecture number 31, chapter number 3 and grade 11. We started bond energy, and which is going to related with the ionic character of covalent bond. In the previous lecture I told you how the ionic character is going to be established in covalent bonding. So we have one example, and we have to confirm from the calculation that hydrogen chloride molecule has an ionic character. It has a polarity. So there the calculation here. Step by step, I am going to start this calculation. And dear students, hydrogen chloride has a 1:1 ratio hydrogen and chlorine. So hydrogen atom is formed by the dissociation of bond between hydrogen and hydrogen. Bond energy of the hydrogen. So written here is 1. Bond energy of 1 mole of hydrogen bond is 436. Bond energy for 1 mole of hydrogen 436 kilojoules per mole. Then you are going to break the bond between hydrogen and hydrogen. You need 436 kilojoules per mole. Means which is equal to 6.022 into 10 to the power 23 moles. Which is equal to 6.022 into 10 to the power 23 moles. Now it means 436 divided by Avogadro's number. 436 bond energy of hydrogen means this hydrogen must be equal to 436 divided by 6.022 into 10 to the power 23 kilojoules. So when you divide, the answer comes 72.42 into 10 to the power minus 23 kilojoules. Because this 23 plus, which is denominator, so you have to change into numerator, so the sign is going to be changed. So this is the calculation of bond energy for the contribution of hydrogen atom. Now, in the HCl, I told you the ratio of hydrogen and chlorine is a 1:1. Means that this value can be divided by 2 to make a for 1 hydrogen. For 1 hydrogen. So for the 1 hydrogen atom, so the bond energy will be half 36.21 into 10 to the power minus 23 kilojoules. Like this one. This is step number 1. In this step number 2, we done for the hydrogen. Now I am going to do for the chlorine. Same procedure. Bond energy for 1 mole of now chlorine. First we done for the hydrogen, now you have to do for the chlorine, and chlorine the energy is 242 kilojoules per mole, and 1 mole of the everything is equal to 6.022 10 raised power 23, like this one. So same procedure for chlorine and chlorine. 242 divided by Avogadro's number. This will be equal to 40.19 into 10 raised power minus 23 kilojoules. This is for the hydrogen and for the chlorine and chlorine, and after dividing this by 2, the same as I done for this one, after dividing by 2, so you will get 20.19 into 10 raised power minus 23 kilojoules. 20.09, and this is the 30 point. This is for the hydrogen, this is for the chlorine. We are confirming that in between hydrogen and chlorine there is a polarity, polar covalent bond is established, and it has some ionic character. Means hydrogen bears partial positive charge and chlorine bears partial negative charge. That's why I am going to explain this by calculation, that hydrogen and chlorine 1:1 ratio. So from where does hydrogen become by the dissociation of molecule bond energy between hydrogen and hydrogen, which is 436 kilojoules per mole. 1 mole is equal to Avogadro's number. Then I divided by the Avogadro's number, so we will get this value. Because I need 1 hydrogen atom, for 1 hydrogen atom I divide by 2. So for the hydrogen 36.21 into 10 raised power minus 23 kilojoules. Likewise for the chlorine, 1 mole chlorine 242 kilojoules per mole. 242 divided by 6.02 10 raised power 23 kilojoules. So this will be a 40.19 into 10 raised power minus 23. For 1 chlorine atom divided by 2, you will get 20.09 into 10 raised power 23 kilojoules. Now you have the value for the hydrogen and chlorine. Means you have to add these two values. So after addition of these two values, 36.21 into 10 raised power minus 23 plus 20.09 into 10 raised power minus 23 kilojoules. So if we add these two values, you will get 56. 56.3 power same kilojoules. 56.3 into 10 raised power minus 23. So students, the value, energy of value should be like this. So we have to omit the power. This power going to be omitted. How? Multiply by Avogadro's number. You have to multiply by Avogadro's number. So for the hydrogen and chlorine, 56.3 into 10 raised power minus 23 multiply by 6.022 into 10 raised power plus 23. So these powers cancel, and the answer you got 338. 338.93 kilojoules per mole. This is calculated value. This value is calculated value. Bond energy of hydrogen chloride is 338.93 calculation. From the calculation what we got this. Dear students, there are two values. One is the observed value. By using spectroscopy technique, instrumentation, so this is called observed value, and that is a very much accurate. And other means calculation, we made calculation this one. Then we compare these two values and take a difference. Much more difference taking place between the calculated and observed value means more polarity show. More polarity will show this one. And I read the table in the previous lecture, and also I will see you here. So this is the calculated value. The relationship between bond energy and electronegativity can be formed by the theoretically. This is a theoretically, and other one is experimentally, actually, and experimental determined value of HCl for the bond energy. So experimental value are we called actual value of HCl bond energy. Actual value of hydrogen chloride bond energy which is determined by the experiments, that is 400 36 kilojoules per mole. 436. Kilojoules per mole, this is the actual, and 338.93 is for the we calculated. So you will see a significant difference between the both. So when you will get a more difference, the bond is a more polar. I told you in the previous table, if you go back, bond energy, the table is given here, and I told you this bond energy in the kilojoules per mole. Hydrogen fluoride is a 567, and the difference of electronegativity is 1.9. If you calculate for the hydrogen fluoride by using this method, hydrogen will be same, and instead of chlorine you have to write for the fluorine. The value is 567, that is actual value. For the hydrogen chloride, this is 431, but the 436 is actual. The difference is 0.9. So this 0.9 difference tells that this is less polar than hydrogen fluoride. And when you calculate the ionic character for the hydrogen fluoride by using this method, so this you will find much more difference than the hydrogen chloride. You will find this a 338.93 theoretical, and actual is a 436. That difference. See the difference of these two values. And if you calculate for the hydrogen fluoride, so you will find much more difference. So this shows that the bond is more polar, there is more polarity. So written here, the experimentally determined energy is significantly greater than that of the calculated one. Yes. Significant difference is given here, 436, 338. This stability is due to the ionic character present in the HCl bond. This difference of two energies of same molecule shows that there is a ionic character, means hydrogen has a partial positive and chloride has a partial negative charge. So this difference is a significant. The amount of additional bond energy depends on the electronegativity of two bonded atoms. Already I told you 3, 2.1, 0.9 difference. So this 0.9 difference shows that partial positive charge bears on the hydrogen end and partial negative charge bears on chlorine end. So it shows a polarity. Greater the difference of electronegativity between two bonded atoms, greater the ionic character. Already I told you for the hydrogen fluoride. Between hydrogen fluoride, this difference is a 1.9. Just like in the previous lecture I explained. So this hydrogen fluoride is much more ionic character. Hydrogen bromide less, hydrogen iodide the least. So from this calculation, we got the result that when you make calculation for the bond energy and experimental value, compare these two both values. If you will get a high difference strong. And if you get the less difference between these two values, this means that this will be a less polar, less polarity. So if you calculate for maybe in examination, he said for the hydrogen iodide, calculate for the hydrogen iodide. So same procedure, then between hydrogen iodide you will get least difference because it has a least ionic character. Difference of electronegativity is a very small indeed. So it has a less ionic character, least ionic character. And hydrogen fluoride has the highest ionic character in hydrogen halides. So dear students, this was a calculation, and there is one table that the comparison of the experimental and theoretical bond energies, as I told you. This calculation is given here in this table. Hydrogen halide for the hydrogen fluoride, fluorine only, that is a 293. 293. Between fluorine and fluorine 155, between chlorine and chlorine 242, between bromine and bromine 193, between iodine and iodine is a 151. Bond energy between fluorine, fluorine, chlorine, chlorine, bromine, bromine, iodine, iodine is the first horizontal boxes. In the hydrogen fluoride, calculated values of 293. If I made calculation for the hydrogen fluoride by using this method, you will get near about 293 kilojoules per mole. Experimental values are very high, 567. Observed value, this is the observed value, experimental value, it is very high. And you will see a log difference, 274 difference. So much more difference you are finding here. In the hydrogen chloride, 338 something and 436 or 31. So near about 95, 92 like this one. And if you make calculation for the hydrogen bromide by using this method, so you will get a 311, means theoretical value for the bromine, hydrogen bromide will be a 311. And observed value is a 366. So difference is a 55, less than hydrogen chloride. So less polar, it is a less ionic character. Hydrogen bromide has less ionic character as compared to hydrogen chloride. For the iodine 151 and hydrogen iodide calculated value is a 291, observed value is a 299, the difference is only 8. The difference between these two energies are only 8, very small indeed. This smallest value indicates that between hydrogen and iodine, least polar bond, and it has a very less ionic character as compared to the hydrogen fluoride. That's the hydrogen fluoride has a highest ionic character. So it is greater than hydrogen fluoride, greater than hydrogen bromide, greater than hydrogen iodide. So hydrogen iodide has a least ionic character and hydrogen highest ionic character by seeing the difference of electronegativities in the previous table I told you, and by using the comparison of the bond energies calculated and observed or actual value, experimental value for this. So dear students, this is about the bond energy and how it affects the polarity of molecules. Highest the bond energy, highest the polarity, and highest the ionic character of the covalent molecule. So now the other topic is bond length. Bond length. So, dear students, bond length is another indicator for the polarity of molecules. You done in the very introduction. Shortest the bond length, stronger the bond, more polar and high ionic character, more ionic character. Short the bond length means bond is strong between the two bonded atoms. This is the bond length, distance. Bond length means the distance between two bonded atoms. And you know, very small indeed. So we use the units, maybe in the angstroms, nanometers, like this one. So bond length means distance between the nuclei of atoms joined by the covalent bond. This distance between the bonded atoms is not constant because the bonded atoms always vibrating with respect to each other. They are going to be vibrating, sharing with each other, not constant, always. So that's why this varying. We take the average. Therefore, average internuclear distance is considered as a bond length or bond distance. Average. I am repeating again, the distance between the nuclei of atoms joined by the covalent bond, and the condition is given, this is not a constant. It varies because the bonded atoms are always vibrating with respect to each other. So due to the vibration with respect to each other, that is why this value is not constant. So that's why we take average. So thus the bond length may also be defined as internuclear distance when the maximum possible overlapping of concerned atomic orbitals occur. Internuclear distance. Internuclear distance when the maximum possible overlap of concerned atomic orbitals occur is called bond length. So we have different techniques to measure the bond length. One is called an X-ray diffraction technique, neutron diffraction technique, microwave spectroscopy. Three techniques are given in the book. One is called X-ray diffraction, neutron diffraction, and microwave spectroscopy. These three techniques can be used to calculate the bond length between two bonded atoms. So it is going to be measured in, I told you, in the form of nanometers. 1 nanometer is equal to 10⁻⁹ meters. 1 angstrom minus 10 meters. 1 picometer minus 12 meters. So in these units, usually we measure the bond length. It is observed that this measurement may vary in accuracy, but still similar bonds are rarely. Because in the similar bonds, chlorine, chlorine, hydrogen, hydrogen, like this one, single covalent bond, and two similar nucleus involved, similar atoms involved, single bond, more accuracy taking place. Two conditions. One condition is that between the two similar atoms bonding, and second is a single covalent bond, because if there are multiple bonds, one is sigma bond and there is pi bonds difference. Just like oxygen, okay, these two atoms are similar, but one is sigma bond and there is pi bond, so there are two different. So dear students, if you want to calculate exact and constant, then the condition is that between the two similar atoms and single covalent bonded atoms. So you will get generally constant bond length. Variation generally being less than 1% if you are taking these two conditions which I told you. Carbon, carbon, single bond. Same atom, single bond. 1.54 angstrom. Carbon, carbon molecule in ethane, 1.54 angstrom. Ethyl chloride, chlorine, carbon bond and between the carbon and chlorine different. That's 1.55 angstrom. 1/2 of the bond length between the two nuclei similar atoms joined by the single covalent bond is called covalent radius. Covalent radii. Covalent radii means the 1/2 of the bond length between the nuclei of two similar atoms joined by the single covalent bond is called covalent radius of an atom. So carbon, carbon, if you have 1.454, if you divide by 2, you will get half of distance 0.77. So this is half of the value by 1.54. So for the hydrogen 0.28, for the carbon 0.77, for the nitrogen 0.75, and so on and so forth. Fluorine the 0.72, iodine the 1.33, and the covalent radii is used to calculate the bond length between the two unlike atoms. In case of equal sum of the covalent radii, carbon, chlorine, in methyl chloride is the 1.76. So all these values are given and you have to add. Just like you have a carbon and hydrogen, the bond length in angstrom is 1.07. Carbon and bromine 1.93, carbon iodine 2. Carbon chlorine 1.76. Like this, carbon fluorine is the 1.38. So students, these are the bond lengths between the two bonded atoms, similar and dissimilar. So average single bond length of some important covalent bonds are going to be formed. This is given here. This bond length also affects the hybridization. sp3 hybridization in methane. So bond length is 1.11 angstrom. If there is a sp2 hybridization in ethene, so so less decrease, bond length decrease. 1 because 1 pi bond, 1 sigma bond, 1.10. sp hybridization 1.08. It means that when the p character decreases, the bond length also decreases. Bond is more strong. Carbon on oxygen 1.41, sp3. Carbon oxygen double bond, sp2 1.34. Carbon nitrogen sp3 1.47 and carbon nitrogen sp2 1.36. So hybridization also affect the bond length. Same as that, double bond, single bond, triple bond, the bond length is also going to be different. So carbon-carbon single bond 1.454, double bond 1.38, triple bond 1.19. So triple bond length is shorter, stronger bond. As you done, as you see in other cases also. So dear students, this is the bond length, and we done the ionic character. So only one topic remains behind, then I will explain another chapter. So this is very important. And next inshallah topic I start dipole moment, there are calculation. You should have your calculators, must calculate these, and these will help you in the calculation for the polarity of the molecules and how to calculate the ionic character of the covalent bonding. So thank you very much.